Thank you, Lucas. Thanks for the nice introduction. Hello, everyone. Welcome to this beginner-friendly talk about strong typing and in particular about strongly typed containers in C++. Before we jump into the details and we have a look at the agenda, let me quickly introduce myself. So my name is Sándor Dargó. I work for Amadeus. We also have an office in Erding, so maybe you already know the company. We are in the travel and hospitality industry, so probably that's why I also like to travel, though these times it's not so easy. So I've been working there for almost 9 years, and I'm working on security solutions nowadays as a principal engineer. If you want to contact me, you will find all my contacts on my blog, where I post almost every week, mostly about C++, but also about the books I read. And well, there's a fair chance that my kids will run in during the talk, we'll see. So that's enough about me. Let's have a look at the agenda. So first, we are going to discuss about strong typing, what it is, what kind of problems strong typing solves. And then we'll see how we would use a strongly typed container. And then we really get into details about how to implement one. We'll see different strategies. Don't be afraid. Don't be afraid when you will see the first proposal. Wait until the end. And we'll also see what kind of open source solutions do we have at our disposal. And at the end, we'll see, okay, with all that, what can we do? What shall we do? So that's about the content of today. It should last about an hour without the questions. I will ask at certain points if there are any questions. Just for you to know, right now I don't see the chat. I don't see the questions, so I will rely on Lucas for that. So why this talk? Why did I want to share these thoughts with you? If you go to C++ conferences these years, you will see that strong types, well, they are quite coming into the mainstream. You will find at least 3, 4, 5 talks at every bigger conference just about strong typing. Still, if I look around in the teams I've worked, or I check the different code bases I contributed to, it seems that still many people don't know this concept. They are not aware of the concept, and they don't practice it. So I'd like to change, well, I'd like to help changing that. And I'd also like to avoid some misconceptions about we might have about strongly typed containers that we might have. You will understand what I mean exactly in a few minutes. And I'd also like to encourage you to use strongly typed containers outside of code exercises, because so far I've seen, except for a couple of cases, that people tend to use them at coding dojos when they work on some code katas, but otherwise they're a bit afraid of introducing these containers, let's say in production code. So, what is strong typing? That's the first question. It's a very handy technique to make your API safer, and also to make them harder to misuse. And you can add specific meaning to your types through their names. We'll see a few examples for that. And therefore, will increase the readability of our code. You can increase the readability of your code, which I consider very important. If you consider the definition of structural software quality by CISQ, Consortium for Software Quality, you will see that readability is one of the 4 pillars of code quality. I know that there are people, and probably there are people like that in the audience right now, who think that, okay, if I introduce strong types, I add some more indirections, I increase a bit the compile time, maybe the runtime. That's true, and that might be true. And performance is also part of the 4 pillars of software quality. But until we don't have a problem with performance, I strongly believe that we should focus on the readability and enhance the quality with that. And stroke typing is a good technique for that. So let's have a look at an example. We have this car class which has a constructor that takes 2 integers. One for the performance, so horsepower, then you have number of doors. I know this is very simplistic, but it fits the slide and it's kind of good for representing the problem. It also takes 2 booleans, which well, is not very great, right? To determine whether the car is automatic, it has an automatic transmission or manual, and if it's electric or not. So what's the problem here? If we have a look at this instantiation, then you see that, well, we pass 4 parameters, 4 arguments, 96, 4, false, true, and you have no idea what these mean here, unless you look up the constructor. You look up the code, you look up the documentation, and say, okay, 96, it must be the performance. Okay, it makes sense. 4 can be the number of doors. It also makes sense. Then false, true. Okay, so probably it has a manual transmission and is an electric car, which is probably a strange combination. So what's going on here? Maybe I messed up, wasn't true. Maybe not. Well, it's really difficult to know, and that's the main problem here. We take parameters of the same type next to each other, and it's really hard to find out their meaning. So what can we do? Maybe we could add some good variable names. So okay. 96 is the horsepower. We can see number of doors. Okay, we see that here. Okay, it's automatic is false. Is electric also false? So when you instantiate your car, it's a bit better because you see what you pass in, but still you can easily mess up the different arguments. Nothing will happen if you swap is automatic and is electric, and I had to see if I swapped it accidentally. It seems I did not, but that's only by chance. And this is well, practical mostly with this compile time values, but when you are passing around parameters between different functions, it becomes more difficult to track down what is what. So we have this problem, and what can we do to solve it? Strong typing. We can use strong types, and they will really help us to increase the readability and, in fact, even the safety of this code. So you see now we take a horsepower type, a doors number type. Instead of the booleans, we take transmission and fuel. They are enumerations in this case. And now you say that, okay, that is actually much nicer, much more readable. You really see that, okay, we are passing in horsepower, we pass in 98. We do the same with the doors, and well, then you have the enumerations, and it's just much more readable. Plus, if it's implemented correctly, you cannot mix up these arguments here, because you would have compile time error, which is great, and that's one of our main goals here. So we have no more misunderstanding with this, and now let's have a look at the simpler implementation for such a type. It will be really simplistic. So you take we take the concept of the horsepower. I don't mean the C++20 concepts. So we just create a class horsepower, and we really just encapsulate here a double, which is probably not the best solution. So we encapsulate a primitive value here, and this is already kind of meaningful, kind of helpful, without adding any further features. Because with that, we won't be able to mess up the different parameters. But you can also add some business logic. And actually, this can be a nice step forward towards a good domain model that you might want to build. So here you might say that the core guidelines, especially this C131, it says that you should avoid the trivial getters and setters, but it's not that case here. And here the name already brings the value. So C131, this anti-pattern of exposing getters and setters for all the members, is really about that. When you have lots of members in your class, and you just by default expose everything, and you make everything mutable with setters, and you don't build up a good hierarchy of objects, and responsibilities are not clear. So this is not that case. Here you really want just to add meaning through the name, and that's it. In case you start to add some business logic, this might become a bit different, and maybe you would even get rid of the getter. So you either keep it stupid simple, like we do in this example, and like we'll do in the various examples during the next 50 minutes or so. And the other option is that you might start adding some logic. It might handle some class invariants. You can check if values are okay. So, for example, if we had a strong type for the number of doors, probably we could check that it doesn't have a really unrealistic number, like 98 is probably a bit too much for car doors, but okay, I'm sure that there are some strange vehicles out there. I think you get the idea. So how could we translate this to containers? So let's take an example without the strong types. We have a player, and the player has a name and many other attributes, but we don't care right now. And then we have a vector of players. We have a small squad. Well, it's not a lot of players, but they are quite good, even if they have some difficult days, at least a few of them. And how could we translate this? So we would have a squad class, and we want to instantiate it the very same way as we instantiate a vector. And we'll figure out if we have to inherit from somewhere, if, well, obviously we'll have to implement the details of the class, but how? That's the question. And also, let's see, how would the call site change and how it would help us? So here we had this function register squad, and it takes a vector of players, and we call it a football squad. Then what happens if we create another container, basketball players, and we try to register them as a football squad. Well, actually, it would work because well, the code doesn't recognize if it's a football squad, if it's a basketball players, collection of basketball players. It's just a collection of players after all. You can register any kind of squad, and that's something we want to avoid. So actually, we would take a football squad, and that would be the name of the type. We instantiate it with the players. Where you might imagine that you can even have football player type and basketball player type, whatever player type, and you can register the squad like that. And with basketball players, with the basketball squad, it just wouldn't work if it's implemented correctly, of course. So let's see, why is this useful? Why is it better to take a football squad instead of collection, a vector of players, which we call a squad? So here, we make the expectations pretty clear, because, well, one could use good variable names, which we used in the previous example, but for example here, you just see a squad. You don't even see a football squad. We forgot about it, but we really have to use the right type names. Well, you cannot just put there anything. Well, okay, you can put there auto, but then that's a different kind of talk, and even that you shouldn't just do. You should apply some constraints with C++20 now. But again, that's a different topic. So we can also, you see, we cannot use the wrong type here. And you can't mix up the arguments, which is valid if we take multiple ones. Multiple arguments. Here we have only one. So like that, we have fewer opportunities to misuse the API. And as mentioned earlier, we could actually move some checks into these strong types. So for example, we could check in a constructor if the size of the players, I mean, the number of the players is enough. Because if we can't go out to the pitch with at least 11 players, well, maybe we shouldn't even try registering a squad. And we could centralize this kind of error handling. We can define these invariants. It's a really nice way to do it with strong types and with strongly typed containers. So the question is how to implement all this. But now let me ask a question. Lucas, do we have any remarks or questions in the chat? We can't hear you.
Okay, then let me ask a question. There was a question in the chat, and I admit this is my own question because this is a fascinating topic. Default arguments. Default arguments, there is indeed people with very strong opinions about default arguments. My question is now, is this something that strong types help with? So basically, what's your opinion about default arguments in combination with strong types? Should I use default arguments, or should I prefer function overloading, or is this both, or does it depend?
Oh, that's a very interesting question. To be honest, I didn't really think about it while preparing this talk. So if I just ignore the strong types here, and I consider all the discussions we had during the recent years, I found really different opinions, and it really depended on what kind of project we worked on. If we worked on a library that was, let's say, distributed in the whole enterprise, or maybe even outside, we tended to not to use default values at all, to well, not to expose the default values, and also to break or ABI more, well, to break our API less frequently.
Yep.
But when we worked in just some internal projects, I mean internal, so let's say we build a server for us, then we tend to use the default arguments because we don't really care about those considerations that I just mentioned. And I don't really see why would it be different for strong types.
Okay. So I relate this to the first example. So the int bool bool, I forgot how it was exactly, but I think it was an int bool bool. In this particular case, a default argument might easily introduce more problems because people forget that there is something in between. It's the usual, I switch arguments even more easily than I do it right now. One argument against default arguments. But now with strong types, this cannot really happen. So I just wanted to hear your opinion. But if you didn't really think about it, then of course we can go on. And there's another question in the chat, which I think might be interesting. So I just read what Ayman has written. Using templates in a register squad, will it break the constraints of registering just the football players?
Using templates in the register squad, will it break the constraint of registering just the football players? I try to understand the question. Well, to me, it depends how you implement it. It depends what kind of constraints you define. It's quite probable that you will just require that, well, it should be a kind of a squad, and then you either break it with all the different squads or not. And if it already requires a football squad, then do we really talk about a template anymore there? So I'm not sure.
Right. So then I just suggest that Ayman is making the question a little more specific. Perhaps this might help. Yeah, please re-ask if the question is not answered. Okay, but that's it for now. So let's continue. Thank you.
We can discuss after if. Okay, so we were here. How to implement all this? And the first option is inheriting from the STL. And I can already hear the uproar that, whoa, maybe you should not do that. Well, if you go out to the internet and check the opinions, you will find very, very strong opinions, stronger opinions than strong types here. So, should we do this? How would it look like? Well, we inherit publicly from a vector of players, and we basically just import here the constructors of a vector, and you see that, well, we can create our squad the way we wanted. We have the different operators that we want. We have comparison. We can use it as a vector. We can use pushback. We can use whatever. So this is something really easy to implement. The interface we inherit from vector, so we have no work to do with that. And our code is readable. So the question is this dangerous? Because probably that's what you are thinking about now, but that, I heard that we shouldn't do that. So why? It's because of the lack of virtual destructor, and which might lead to undefined behavior. Now let's think a little bit more about this. And we have to say that possibility is not certainty. So the CERT guidelines say that do not delete a polymorphic object without a virtual destructor. Because if you delete an object through a pointer to a type without a virtual destructor, then you have undefined behavior. And that's really something we want to avoid. So you should really not delete a strongly typed container with a pointer to its base with a pointer to the vector. But to be fair, we said, okay, it's a possibility. And that possibility can be avoided quite easily. So you see here on the left side that, well, we have a pointer to the vector and we delete it. Now this is undefined behavior. Well, you just don't do that. And then you avoid a problem. And, well, it's easy to say that you just don't do that, I know. But you can consider a couple of things here. One is that, well, you want a strongly typed container, you want a football squad. Why would you delete it through a pointer to a vector of, well, here I put integers, I should update it to players, but why would you do that? And then you can also think that, okay, Hiram's law says that if we expose something in our API, then we can really rely on that it will be actually used and someone will use it, and that's kind of a danger, and especially in an environment where people come and go quite frequently, like in corporations. Having something like that exposed, I think, is really a bad idea, because maybe not everyone knows that we shouldn't delete an object like that, and for whatever reason, he or she will end up doing so, and we miss a code review, and it just gets into the code base, and God knows what happens then. But there's another thing we can still do here, because I said here that well, why would you want to delete it through its base? You wanted a football squad, but what if you want to manage squads and you want to be able to manage a football squad, basketball squad, whatever? Then we can add actually another layer. We can create a squad with a virtual destructor. And then again, we can avoid the problem on the left side, and you can here you can deal directly with a squad, but still, we still have the opportunity to misuse it, and that's why I will be really afraid to introduce it in a bigger code base. But let's see what other kind of problems we might have with this design choice. Because if you consider how the STL was designed, the idea of Alexander Stefanov was really to separate a kind of a couple of different concepts, types of objects, like the containers, algorithms, function objects, and iterators. They were all separated. They are all separated in the STL. And if you start inheriting from an STL container, you introduce strong types like that, there's a fair chance that pretty soon you will add some kind of algorithms, you will add some kind of logic to this strongly typed container, and you start mixing these separated concepts that the STL is designed upon. So you break that. And I say that, and so, is that a problem? Does it matter that you break the STL design? Well, like economists tend to say, it depends. Most probably, And well, maybe some of you do, but most probably most of us don't develop for the whole C++ community. And we write often code for specific, very specific business applications. And most of this code is not reused at all. In many cases, the best case you can imagine is that someone copy-pastes your code to a different project. So you don't really have to worry about generic design issues if you don't write generic code. Worry about it if you write something generic. And otherwise, well, we just focus on what matters. And while generic solutions need generic design, but otherwise what we need is maintainability and readability. And for that, you want to keep your code clear. And you want to make your API easy to use and hard to misuse. And there's a very good talk on that by Matt Godbold, by the way. I shared the link somewhere for the talk. So what about inheriting from the STL? Is that a good idea after all? Well, we saw that it's easy to implement and it gives us type safety. We have problems with the lack of the virtual destructor, and that also gives a possibility to misuse our API. So you really have to pay attention how you use your strongly typed containers if you start inheriting from the STL. And it's definitely not something I would use for libraries. And as I said, I wouldn't even recommend it for bigger projects. Maybe it can be suitable for prototyping some concepts when you just really want to have a strongly typed container quickly, and you don't want to deal with it, and you know you will throw it away. But be aware that most of those proof of concepts, they end up in production at the end. So beware of the problem. So we'll see another option, which is kind of an outlier using an alias. Why do I say that? Because we could actually just use an alias here, either with using or with typedef, and well, as basically we still talk about just a vector of players. Obviously, we have the same interface as of a vector. This is something very simple to do. We have of course, we have the interface. The code is still readable, but this is not strong typing, not at all. But still, this might be a good step forward if you just want to introduce some better names. But be aware that this is not strong typing, so you can require a squad, but then you will just pass in a vector of players, and whatever players, it will work. We don't have standalone types, we just have more readable type names. And one thing we wanted is increasing the type safety, and actually we don't have it here. So is this a good idea? Depends. It's something easy to use, and it already increases readability. So you see, this basically comes for free, but the readability of your code will be improved, though it doesn't give any protection. So should we use it? Well, maybe. Maybe if you just want to move forward towards more readable code base and better names, but you don't have the time to implement strong types right away, then you might consider it. Now let's move to the third option, private inheritance. And first, maybe we should discuss what private inheritance is, because that's not something we use frequently, and I think there are good reasons for that, as we'll see. So, just as a reminder, the access specifier of the inheritance doesn't affect the inheritance of the implementation. It's always inherited based on the function's access level, but the access specifier here affects the accessibility of the class interface, which means that private inheritance is more like a composition. It more represents a has a relationship, not an is a relationship. And you might consider it just as a syntactic variation of composition that we'll talk about after. And the core guidelines is quite open on this question. It says you should use composition whenever you can, and private inheritance when you have to. But still, there might be some reasons why you would consider private inheritance. We'll see in a few slides. But first, let's see what the core guidelines say when you should use private inheritance. And I didn't really like the example that I found on core guidelines with Fred and Vilma and Barney, I think. So I tried to come up with something else, but I'm not completely happy with that either. And that's pretty much shows how difficult it is to find a good use case for private inheritance. So we have the derived class that has to call non-virtual functions of the base. And you also need the base that has to invoke usually pure virtual function of the derived. So let's see. We have a class of road. You see I really use the cars here everywhere. And it inherits privately from an engine, which seems really awkward, to be honest. But if you consider that it's not an is-a, but a has a relationship, then it makes a bit more sense. And it has this public interface of accelerate, which calls the engine. You see here we have a protected non-virtual invoke accelerate, which for some reason it notifies the power user. And that's something that has to be implemented by those who inherit one way or another from engine. So my opinion is that if you really have to use this for the use case that is explained here on the left and on the core guidelines page, then you have some design issues, and you should rethink your class hierarchy completely. But it's worth knowing that using private inheritance is also possible, and it's an option in some cases. So how would it change or strongly typed container? So now we inherit privately from the player vector, and well, you see we have to expose or implement whatever we need. So it's still simple to implement, but as the interface is not inherited, we'll have to type a lot. We will say import all these functions, all the functions that we need from the base. So probably we need the constructor, we need the pushback, we need whatever, and we also have to implement the comparison. So we'll end up writing quite a lot, but the missing virtual destructor is not a problem here anymore, because we don't even have access to to the private, well, to the implementation, sorry, the interface of the base. We don't have the access to the interface of the base. You saw that I used the using directive, the using declaration here, and I know that this is probably not needed for most of you to talk about this, but I also saw in code reviews that for many it's new, so I just want to take a minute to explain that when you use using and let's say you expose a part of the base class API with that, you gain two things. First, and that's the less important, you don't have to type so much as with forwarding the call, let's say from with this empty to the vector empty. What is more important is that well, it's not very probable with the vector, but if you inherit from something else, if you do some mocking, then it becomes more important. Then let's say that your base class API changes in a way that, well, maybe empty didn't take any parameter before, and it didn't take any argument before, but now it expects it will expect one. Then, if you implement the forwarding like this, then you have to change it. It also has to take that argument, so you have to add a parameter here, and you have to forward it. Whereas if you just use using, you don't have to do all that, because you get all the overloads automatically, and no matter how they change, well, you have them. So using is something way more convenient, both in the long term and in the short term as well. So we saw a bit of private inheritance to implement strongly typed containers. Is this a good idea? Well, you don't have a problem with the missing destructor, and you can use using. You have a linear API. You say you have a linear API because you have to implement all that. You have to type all that, okay, using this and that, using this and that. So we are lazy people. We won't really expose anything that we don't need. So we'll have a nicer API. But still, we have to type quite a lot. And we rely on something that is not widely used, like private inheritance. Probably I could count on my fingers how many times I saw in our production code base private inheritance. Maybe I wouldn't even need 2 hands for that. And now let's check composition. So what's this composition about? With composition, you try to build something complex from simple blocks, and you want to show that you have some members that are part of a whole. And just like private inheritance, composition is also has a relationship, but probably, well, not probably, it expresses it in a more natural manner. But you'll have to type a lot. Here you really have to type a lot, and as you see, as we move forward with the talk, the font size decreases because we have to fit more and more code at the same area. So now we cannot use using anymore. We have to forward really everything. So everywhere I said, okay, this is simpler to do. This is simpler to do. Composition is simple to do. It's not difficult, but okay, it's a bit more cumbersome because we don't inherit the interface in any way, in any meaning, and therefore using is not a possibility here. You will have to type. You'll have to type a lot, and well, maybe it's good maybe it's bad, but no language tricks are used. I tend to say that it's good. It makes our code more readable, easier to understand, even if it's a bit longer. So here I really think that we'll end up with the leanest API possible, because well, nobody will type all these for you. You'll have to do it yourself, and you will try to implement the least necessary. But you will have to forward some of the calls. It's possibility that you won't actually forward just like that, and you might end up with something more customized, but then it gets more difficult to use it as a container, as you don't use the same names. But you will really end up forwarding only what you need, and you will end up with a nice API. So I think this is really good for internal projects, but might be problematic for libraries if you cannot really foresee how people want to use your strongly typed container, or you will do all the typing up front and you make sure that you just expose everything that the container has. And you also have to think about the iterators, something we haven't discussed yet. So we have to expose them one by one. At least we can help ourselves and future maintainers and the users as well to use an alias for the iterator, so that let's say your clients won't have to change the code, and actually you will have to change it less as well if let's say you replace the vector with the list, with the deck, with whatever. Still, the clients will have to recompile, but it's I think it's not that big deal compared to actually having to update the code. And at the end, with exposing all the iterators nicely, you will be able to use your strongly typed container as a real container, like with standard algorithms. So shall we choose composition then? It's intellectually simple. I think it's much simpler than private inheritance. You have the option to fully customize your API, and you have no problem with the virtual destructor in any way. But you'll have to do lots of typing. That's the price that we have to pay here. So which way should you choose? Which way should we take? Can we give any meaningful advice here? So I think that if you have no time, and it's quite often the case that we have very limited time, but we want to make our code a bit more readable, then we can consider just aliasing, which is not, I know it's not, we don't introduce strong types at all, but we already increase the readability, and it can just show the way forward, and later on we can introduce the strong types behind those aliases. If you want to do some prototyping, you have some very small projects, I think inheriting from the STL can be a good enough option, but beware that small projects can grow big, and often prototypes end up in production. So be very cautious when you want to inherit from an STL container. I would definitely not even consider it for bigger projects or public libraries. And if you want to express a bit more meaning with strongly typed containers, if you need strongly typed containers, go with private inheritance or with composition that don't have the aforementioned problems and give you more safety, but you have to prefer composition over private inheritance. That's what also the guidelines say. We saw or reasons. It gives more flexibility. It's I think it's easier to do it in a correct way because it's simpler intellectually, and yeah, it's just more understandable for the readers of the code, for most readers of the code. So before we have a look into a couple of open source solutions, let's see if there are any questions. Not sure who I should ask, Lucas or Klaus.
So this time it's me again.
Hey.
There are no further questions.
Mm-hmm. Okay. So let's move to the open source solutions. I had a look around what kind of solutions are out there, and I picked 4 open source solutions. These are the 4. So we'll see TypeSafe by Jonathan Miller, NameType by Jonathan Bocher, StrongType by Björn Fowler, and StrongTypeDef by Anthony Williams. And you see that there's a bit of space between TypeSafe and the other 3. And you'll see why is that. So the similarity is that we speak about all header-only libraries, and they are quite well documented. Honestly, I would be happy if all corporate projects were so well documented as these rather small libraries. We'll see that 3 of them are very similar, and they are quite easy to use. That's why there's a space between TypeSafe and the rest. So these 3 are quite similar, and one offers a bit more customization. It's TypeSafe, but still, it's also easy to use. You will see. Now, when I first shared this talk last week internally in the place where I work, many people asked at this point, okay, why don't you speak about Boost? Why don't you speak about Boost Strong TypeDef? And well, probably I should have spoken about it, but there are a couple of good reasons why I skipped it. So if you look around on Google and check some discussions with the author of Boost Strong TypeDef, he says that, well, look, it's not a first-class Boost object, and it was only implemented to help his work on serialization. He didn't mean it to use it just everywhere as a strong type. He did the least necessary that he needed for his own purposes. So with that, you will see that it doesn't always meet some essential expectations that you might have. And compared to the others, which are quite well documented, this is not. Because it was not meant to be something it was not meant to be a first-class Boost object. That's the reason. So here you see that with and who wants macros anyway in 2022? But joke aside, you can create your strong types like timer ID, process ID with this Boost Strong TypeDef macro. But depending on the C++ version you use, and depending on the underlying type that you use, you might end up in a situation where you can compare these 2 objects, okay, TID and PID, the timer ID basically and the process ID, and they will be considered equal, and you can just easily sum them up. And this is clearly not what we want. That's why I don't talk more about Boost strong type def. It was meant to solve a specific issue, and it solved it very well. Now, it's like Hiram's law. It's exposed, so people will rely on it. But if you are looking for an open source solution of a strong for a strong type, don't pick this. So let's see, how does type safe look like? We'll have our player struct everywhere. It has a name. Here we have this comparison operator equals equals. And let's see how we can implement our strong type. So you see that we have to actually create a type here. It has a little bit of overhead, let's say, because we manually create this class and we inherit from this strong type def from the TS namespace. And you can see that we use a quite popular modern design pattern, curiously recurring template pattern. So what it means here is that we have the derived class squad, and we pass it as a template argument to the base class. So you see that's the first argument we pass in. And then, okay, there are some building blocks available, which is really nice. It's a really nice feature of all these open source libraries that we are going to talk about. So, and I think like all of them is relying on CRTP, and they use this way to enrich or strong types that you can mix in. You can mix in some behavior, like you can mix in here equality comparison, and then we can compare two squads quite easily. And you see here what we still have to do is to expose, to import the constructor of strong type def, the constructors of strong type def, and we almost have the very same way of creating our squad here, but you see we have an extra pair of braces. And how can we get our type? Well, how can we get the underlying vector? Well, with a static cast, or we can actually have a get function. We can implement it on our own. You see on the next page that well, you can encapsulate that static cast, and you can expose that vector. And actually, this is the only library of the four that offers a really flexible API, because, well, you have your own struct here, you have your own class, you do whatever you want. The downside is that it needs a bit more typing. So now we move to name type by Jonathan Bokhara. And here you see that we have a very similar player struct, and we are just aliasing basically here a template specialization of named type, the Fluent namespace. So first we pass in the underlying type. Then there is this squad parameter, which might seem strange, and you might want to ask, okay, but where does it come from? But actually, you just declare it right here. Sorry, and with this, you make sure that if you have two strong types, both with the same underlying type, they won't be considered they won't be considered the same type, because if you use here a unique name like squat parameter, football squat parameter, basketball squat parameter, it will make a distinct type. It will make squat a distinct type from another template specialization. And it also has these nice building blocks. Like you can make things, you can make it comparable. There are many others. So we can we have this built-in get function to access the underlying value. So you see, this is something really easy to introduce. I mean, you don't even have to implement any new class. You really just use this this template, and maybe. But I think all of them have quite good documentation, but probably this one is with the best among the others. Your API won't be really sophisticated because you don't have really a way to enrich it. But that's what you get when you take these free libraries. So now we have a strong type by Björn Faller. And he said that he was inspired by TypeSafe, the first one we saw. But to me, it really reminds me to just the previous one by Jonathan Bocara, the name type. It really looks like that. Actually, you could switch between the two with just very easy find and replace, because even the order of the template parameters are the same. First, it takes the underlying type, then it takes this other struct that makes it different from other strong types inheriting from a vector of players. And you also have these different building blocks like the equality comparison. And what is different though here is that you have some extra functions. You get swap. You can easily access the underlying type. You see, we have this value of that helps you getting the underlying vector. And these are some really good additions that I liked with this library. And probably you end up here with the most readable code because of the names, because of the namespace name, because of the type names, the name of the building blocks, and this value of makes it also be really readable. Sorry. So what you still have as a problem, might be a problem, that your API is still not very sophisticated. And this is the last one, strong type def. It's still really just like the previous two. It looks like name type or strong type. It has extensive documentation, especially with all these different building blocks, like the equality comparable. It documents it really well. You can get the underlying values with the static cast, or you have this member function underlying value, which comes also quite in handy. So these different properties, that's how Anthony Williams called them strong type def properties, they are very well documented. Still, we cannot change much the API. It's the downside of these libs. And maybe to my taste, it's a bit more verbose. I mean, if you consider this JS as strong type def properties, it's a bit long. But That's maybe only me. So, how to choose among these four? So, if you want a customized API, whoops, I clicked on the wrong part. So then you go with type safe. If you want simplicity, honestly, you can pick any of those three. Check the licenses. Some of them are some of them use MIT, some use BSL. All should be pretty much fine, but you might have a preference. And at the end, it all comes down a bit to personal preferences. That's my opinion on them. So, what solution to choose at the end? Should you pick an open source solution for these strong types, or should you implement your own? So, in terms of licenses, you will be fine, I think. But none of these have, let's say, premium support, these open source libraries. I checked in Amadeus with the team responsible for introducing new open source libraries, and they said, look, we cannot take any of these because they are all one-man projects, and they can be abandoned at any time. And then what do you do? So it depends. If you want to rely on the fact that it will be available, that the library will be maintained, then you cannot really pick these, because you might end up in a situation where you are on your own. And in that case, you should go with your own implementation. But otherwise, I think they are really nice and easy ways to introduce strong types and strongly typed containers to your code base. So to conclude, I would recommend using strong types for increasing your type safety and to reduce the chances to misuse your APIs. And remember that with strong types, you can add more meaning through the names, through the type names. So how to start if you haven't used strong types so far? I would advise you to take a code kata and just play around. Maybe you can use bowling, game of life, or poker hands. You will have the links for that. And why do I recommend these specific ones? Because you will end up using containers. So you can practice, say, naturally using strongly typed containers. And spread the information among your peers, your colleagues, your friends to try to use more strong types and introduce them to projects just little by little. And thanks for your attention. That was it. Are there any questions at this point? At the end. Hey, Lucas.
So, first of all, thank you for this wonderful talk. Yes, there are a couple of questions. There's a question by Ofek. He asks, or they ask, do all these strong type libs have zero runtime overhead?
Zero runtime overhead. Not sure if I could say zero. Probably it's not zero, but I do think that as long as you cannot identify that you have a bottleneck because of them, you don't have a problem. And I don't really see these causing you strong performance issues.
Maybe could you, if you notice, could you elaborate a bit on like how they implement it? Because that could affect, right, the runtime overhead, like what strategy, because you presented
they will use the CRTP. They will use the curiously recurring template pattern, so you won't end up with dealing with virtual tables and dispatching.
So then where do you
This
think
is
this overhead comes from?
well, look, you still add a little bit of indirection, and the cost might not be zero, but I think it's negligible. That's what I wanted to say.
Okay, thank you for this answer. And there's another question by Killian, I think. They ask, strong type def libraries, why do I have to explicitly opt in the equality operator? Can't the libraries just always provide it if it in okay, I can't probably read it, provided in a Safari friendly way?
Well, that's probably more a question to the implementers. But if you think about the main idea behind C++ that you don't pay for anything that you don't want to use, well, you might not need equality comparison, and you don't want any code, not even any code for that generated. And if you need it, you tell it. It's just passing one more argument to the base template.
So maybe this coming from like an optimized perspective, but doesn't unused code then get eliminated away? Or is it about like not generating and compiling this code?
Yes, I think so.
Okay. And then I think that's the questions from the chat. So if you have more questions, please ask them. I have two questions personally. The first one is, I remember using some libraries that in some ways had certainly some strong type characteristics, mostly like cryptographics libraries. And I remember using them was quite a pain, mostly for two reasons. One was composability, so like how well it composed with other mechanisms from the standard library and how well it composed with other like building blocks. Another one was like getting data in and out of these like type safe containers or like data structures, because once you had more than one layer of them nested into each other, it was quite challenging because these components were part of a bigger pipeline of like operations, right? It was not the whole code written based solely with this library. There was only some parts of the program, and I remember it was quite difficult to like get data in and out of them. And how can you give some guidelines or advice how one could avoid such problems?
Well, I think that there are no like black and white solutions. So there is no magic bullet. If you solve some issues, you will end up having other issues. So just something you mentioned now, I had similar feeling today. I was working on a library that is, well, it took mostly the aliasing way. And then I read the code and say, okay, but what is this? And okay, I take a key list. So, okay, what's that? Wow, okay, so it's actually a map. And in another case, it's called, I don't know, data list, and it turns out to be a set. So you have this problem that if you introduce strong types, then you lose the you lose the meaning of the underlying type name, and it maybe becomes a bit more difficult to figure out how to use it naturally. That is my feeling. But this is less and less a problem, because with modern IDEs or code editors, often it just hover over the name and maybe even the variable name, and it just opens up the documentation of the of that class. You can quickly browse the API in a small window, and you see what's that. But again, it's still a bit more mental work in that sense. But you end up with safer code. So what I think about this is that, okay, you want to use strong types, then use good names, and at least don't use names that will just make the life of the maintainer more difficult. Like I mentioned that I saw this, okay, kind of a list, data list, key list, and you end up associating it to a list, and you see it's something else. So use I would say more functional names that makes your code more readable, and that is not so easy to misunderstand. And then you will still have to pay the price of looking up the documentation, looking up the API. I think that it's still worth the price, because when you write the code, you have to do that. But when you read it, it seems then it seems natural, in my opinion. So when you read the code and you see that it's used, okay, it's used in a standard algorithm, you see, okay, I have a standard container behind. It's fine. When you have to use them, you write them, you have to look up, okay, what is this actually? What is this type? And how can I use it? But you do that once. And you read it all the time.
Would you, applying this, what you just said, to the examples you gave earlier, would it make sense to maybe call it a squad vec or a player vec, or somehow encode that there's a vector behind it?
No, definitely not, I think, because then well, it's a bit like the Hungarian notation, which was really not meant to be like it ended up in the software engineering culture, and it became infamous instead of becoming famous. So if you start using names like squad vec, well, it's still better than calling it a squad list, and it turns out to be a set. Okay, squad vec is better than that. But still, you expose something that you might not want to expose. You expose the underlying type, and maybe that's not why you started to use strong type in the first place. Plus, what if you decide to change it? What if you decide to change the underlying container, and you move away from a vector to anything else? Then you want to change the name as well? Well, maybe it's not a problem, because again, we are moving towards more modern tools, and if it's something internal, then maybe it's fine. If it's just your project, but as soon as other people rely on it, then it becomes more difficult. So I would just call it as a squad, or football squad, basketball squad, whatever squad. I wouldn't mix in the name of the underlying type.
Okay, yeah, thank you for this detailed answer. And there's one final question. It's about a strategy, like one maybe an alternative to what you described earlier would be composition, and having an implicit or an explicit cast to the type, to the underlying type.
So what's the question with that? So maybe
I'm just curious, have you considered this? Do you know about this approach? Or
well, if you cast it automatically to the underlying type, I think you end up in a situation where you can accidentally swap parameters, like different kind of squads, don't you? If you can implicitly cast it to the underlying type.
Only if you can construct it from that type. It's one way, right? You can cast down, but you can't cast up unless the constructor provides this opportunity.
Well, probably it would need a bit more thought and experimentation. I would say that just thinking about it quickly, if I want a strong type, I don't really want implicitly the underlying type. And here I had quite simple examples, but I would personally move towards more the domain model, where I move some logic to these strong types, and I try to do stuff internally in those classes, and I would need much less the need to actually access the underlying type.
Okay. I think
But
that's it.
it's really difficult to, I think, to showcase those in small slides. When you start moving
I've given a couple talks, and I know what you mean. It's like getting it into something meaningful, but at the same time, like realistic in some way.
Yeah.
I think there's no clear answer.
And
always
that it fits the screen of how we say of everyone, but I mean, there are some examples you cannot even fit on a huge screen. So
exactly. Well, so thank you so much for this wonderful talk, and I hope everyone that listened enjoyed it. And it was great having all these this conversation in the chat. There's now the after talk chat. We will be joining you there in a couple minutes. It's the Zoom link that was just posted in the chat. It's the tiny URL link, but it's a Zoom meeting, so you need a Zoom client installed. I think you can maybe use the browser. So see you there.
See you there. I will join in a couple of minutes, and I think then I can't say stay long, but then in a few minutes after I can come back and I can stay for a long time if you want to discuss. And in any case, you have my name, and there's only my father and me with that name, so you can contact me easily through my blog if you want to discuss.